So hi everyone. So we'll start at our usual time, that is 3 or 5 p.m. So we'll just wait for 5. Kindly mute yourself. So we'll start at our usual time, that is 3 or 5 p.m. I think this is the last live session, so I'm expecting some audience. So we'll start at 3 or 5 p.m. So actually, today I'm at a different location. So in case there are some connectivity issues, do prompt me in between. I hope, although the connection is quite stable, but still, if there are some issues, do prompt me anytime. And also, Kailash, you are joining after so much time. I hope you are watching the recordings. Yeah. I got that. I got that. So we'll start after 1 minute. So it's 3 or 5 p.m. I think we should start. And let me just share my screen first. Let me just put my camera here. So let me just give this introduction as always. So good afternoon everyone. Someone has joined in. So just a second, I'll just put my camera here first. Good afternoon everyone. My name is Musab Rafiq. I welcome you all to this live session number 12 of the course Digital Electronic Circuits. The course is taught by Professor Gautam Saha from IIT Kharagpur. I'm a PhD student at the Department of Electrical Engineering at IIT Kanpur. This is the last live session of this course, and today we are going to discuss problems related to memory organization and operation, memory expansion, memory cell, different types of memory, ROM, PROM, PAL, PLA, and so on. So the guidelines are same as always. If you have any doubts, you can type it in the chat box. But I guess the live audience is not that much. You can use your microphones as well. So this topic is mostly theoretical. There are no such numericals involved. But I have kept some slides where I will explain the operations of SRAM and DRAM, just to give the perspective of that. And also there are some multiple choice questions. We'll be discussing them. And also, if a new participant is joining when I'm solving any problem, I won't be able to admit them that time. I'll just join them after I solve a particular problem. So I think we can start without any further delay. Yeah, I think we should start. So let me just put it here. So we have this question, a pretty simple question. It says that each cell of a static SRAM cell contains, in fact, the words SRAM itself contains the static, so I think it should have been each cell of a SRAM cell contains A 6 MOS transistor, B, let me just, someone is trying to join in, let me just admit the person. So I'll just repeat the question number one. Each cell of a static SRAM cell contains A 6 MOS transistors, B 4 MOS transistors and 2 capacitors, C 4 MOS transistors and D 2 MOS transistors. So it's a pretty simple question and most of you might be knowing the answer to this question. So it's simply 6 MOS transistors. So now let's just shift our attention to this 60 SRAM. So why do we refer to it as 60? So the word 60 means 6 transistors. As you can see here there are 6 transistors. 1, 2, 3, 4, 5, 6. This whole thing is a 60 SRAM cell. Just a second. Sorry for this disturbance. Okay. Now we have this 60 SRAM cell. The core of 60 cell, this whole 60 cell, it consists of two cross-coupled inverters. So which are those? So M1, M2 forms one inverter and M3, M4 forms another inverter. So this thing, this is VDD, this is V in, sorry, this is V out, and this is V in. So this is my inverter, a CMOS inverter, where this transistor M1 is an NMOS transistor and M2 is a PMOS transistor. So this is a inverter, this thing here, M1, M2 and M3, M4 is also an inverter. So the core of this 60 SRAM cell contains a cross-coupled inverter, this one. And it has the data is stored on these nodes Q bar and Q, which are called storage nodes. And the data is represented as charges that are stored at one of the two nodes. Due to the symmetric nature, because of this symmetric nature that we have here, the data pattern is always complement. So if the data stored here is 1, this will be 0, this is 0, this will be 1. So due to the symmetric nature, data stored on these nodes Q bar and Q are always complementary. These storage nodes are connected to bit lines. So we have two bit lines here. This is called as bitline bar or bitline complement, and this is simply bitline. BL stands for bitline, and these are connected to this thing. To the storage nodes are connected to these bit lines via these two transistors, M5 and 6. These are called as pass gate or access transistors. So M5 and M6, they are called as pass gate or access transistors. So here I'll just refer them as access transistors only. So far what we have shown, this M1, M2, M3, M4. So M1, M2 forms one inverter pair. So sorry, one inverter, and M3, M4 forms another inverter, and together they form a cross-coupled inverter. And M5, M6 are, as I said earlier, pass gate or access transistors. And these storage nodes, where the data is stored in complementary fashion in Q bar and Q, are termed as storage nodes, and they are connected to these bit lines BL bar and BL via access transistors. This here is word line, and this here is power supply VDD. We can also draw it like this. In short, we can also draw it like this. If so, we can draw it like, let me just show here. We can have this access transistor here. Then I have this thing. This thing is a symbol of an inverter, and this here is another inverter. Together they are cross coupled. And here is also another access transistor, and here is bit line, and this is bit line bar, and this is connected to word line. Same goes for this, and here because of the space crunch I'm not able to show the bit line. Let me just show it. So these were the things that were present in the 60 SRAM cell. Now let's just briefly discuss, just brief discussion about their operation. Now just briefly discuss their operation. So there are essentially three operations. How many? Three operations. There are three operations in order. Number one is hold. Number two is read. And number three is write. Correct? So what is this hold operation? Hold simply means holding any state. It simply means no read or write is being performed. So no read or any write operation is being performed. And in this case, word line that is here, this word line that is connected to the access transistor is grounded. So in hold operation, no read or write is performed, and this word line is being grounded. Now next we have read. So basically, simply as the name itself suggests, so it means to reading anything that is being stored. So whatever is stored here and here, it needs to be read. So we need to read the state. So now let me just use another slide. I don't want to create a crunch here. So let's just explain read now. I hope I'm audible. Am I audible? Can someone confirm? Okay. Yeah, okay. Thank you. So now we'll discuss this read operation. We'll just discuss it briefly. We don't want to go into details, just a brief introduction here. So let's just suppose 0, we'll assume 0 is stored at q bar and 1 simply because the symmetric nature, as I said earlier, its complement will be stored at q. So 0 is stored at q bar and 1 is stored at q. So we want to read the states. So whenever we are performing the read operations, before this read operation, we need to precharge the bit lines BL bar and BL. So before read, bit line bar, or you can call it bit line complement, and bit line are precharged to voltage VDD. So these are basically here a parasitic capacitances are present and they are charged to VDD, and both are charged to VDD. Now for a read operation, what is happening during read operation? Word line is activated. So what do you mean by word line is activated? Word line is connected to VDD, and as a result of this activation, access transistor M5 and M6 are turned on, and as a result, access transistors M5 and M6 are turned on. Now this left hand side, let's concentrate on this left hand side, this part, M5, M1, M2 part. Left hand side will see a discharge current from bitline complement. So it will see a discharge current from bitline complement to ground through access transistor and this transistor M1. I forgot to mention these transistors M1 and M3, they are known as also called as pull down transistors because they try to pull this node to ground. These two nodes are ground, and these two transistors M2 and M4, they try to pull these two nodes to VDD. These are pull up transistors, these are pull down transistors. So the left hand side during the read operation, this left hand side sees a discharge current from bitline bar to ground through access transistors and this pull down transistor M1. So a discharge current will flow and it will go through this thing, and it will see a this bitline complement will see a discharge. And once it's discharged, because this was pre-charged to VDD, now it will be going to 0. And as an amplifier, we can see that we can look at the difference and we can read the state. This will remain unchanged and this will discharge to 0. Similarly, we can see the operation for when 1 is stored at q bar and 0 is stored at q. So we can see a discharge of VDD at bitline complement when 0 is stored here. If 1 was stored, this transistor would never have been turned on. And also there are things like pull-up ratio. I won't be discussing them here. That's a bit advanced. You can always refer some books if you want to discuss those. Now let's just take a look this at right operation. Take a brief look at right operation. This is just a simple idea. There are other things are also involved. How to maintain the balance and how to not flip the states accidentally and all. And that's going into deep detail as we have time crunch here and we don't want to spend most of the time discussing the concepts, and it's also a bit advanced. So you can always refer to the books. I'm just giving a broad idea to this. Now let's briefly discuss the right operation. So before proceeding to right operation, let us assume q bar was storing 0 and q was storing 1, and we need to write. So write simply here means to flip the states. We need to flip the states. So flipping the states means we need to write q bar to 1 and q to 0. Someone is trying to join. Let me just admit. So okay. Pintu Kumar has raised a hand. Pintu, so you have any question? If not, I think we can continue. So we need to write we need to write 1 at q bar and q to 0. So based on this, what we'll do, we will bias bitline bar to VDD because we want to write 1 at q bar and 0 at q, and we will bias bitline to 0, that is to we will connect bitline to ground. Now for write operation, word line is activated, that is we will connect the word line, it's connected to VDD. So the write operation typically involves two phases. How many phases? Two phases. In the first phase, the write branch. The write branch consists of this block M3, M4, M6. The write branch. So this bit line is grounded. Here initially 1 is present and this is connected to VDD, and this word line is also asserted high. This will be turned on. M6 will be turned on. So the write branch will lead to a current flow from pull-up transistor. So will lead to a current flow from pull-up transistors, that is M4. As I earlier said, this is called a pull-up transistor. From pull-up transistor M4 to access transistors to ground. So this will this lead to a current flow from this, and as a result this thing will discharge. So this thing will discharge and Q will tend to 0. So what's happening? The right branch will see a current flow from pull-up transistor M4 to pass gate transistor or access transistor M6 from VD2 to BL. So this thing is connected to BL, which is grounded, and here will be the discharge and Q will tend to 0. And in the second phase, as Q is tending to 0, so as Q is tending to 0, so this thing is tending to 0, which is the input of this inverter pair, this inverter M1, M2, will lead to the increase in the voltage of Q bar. And also because of this, it was also connected into it was also trying to go up. So there are two forces acting, and this thing will be asserted high. So this thing Q bar will go to 1. Because this Q is tending to 0, this voltage is here is decreasing, and this inverter, because the characteristics of inverter are like this, if you see the VTC like this. So as this voltage is decreasing, V in voltage is decreasing, output voltage is quite raising, and this Q bar will be tending to 1. So this was a brief introduction to this read-write operation of 60 SRAM cells. Apart from this 60 SRAM cells, and as I said in this, while the write operation, we need a sense amplifier. So this sense amplifier is not a necessity, but it just increases the speed of operation. Is increases the speed of operation, and also there are other configurations of SRAM like 80, 9, 10, and 13, and you can just refer to them if you want to see them in details. In 80, basically in 80 SRAM, the read-write path is decoupled, where we have additional word line and bit line for read and write path. For more on this, you can refer to this book by Professor Shimangyu of Georgia Tech. You can refer to this SRAM chapter in detail if you want to go deep into this. But from a bachelor's perspective, this thing is enough, more than enough. So now let's discuss question number 2. I hope there are no questions. Let me just take any questions if there are any questions. Are there any questions? So I assume there are no questions. Let's just move forward. Now the question asks us the minimum number of transistors required to make a dynamic RAM cell is. So dynamic RAM is simply DRAM cell. So the minimum number of transistors required to make a DRAM cell is 1. I also kept a slide for this DRAM because I thought these SRAM and DRAM, they are quite important, and let me just elaborate on these two things. So here towards the left hand side of your screen is this 3T DRAM cell, and towards the right hand side of your screen is the 1T 1C DRAM cell. So minimum number of transistors required to construct a DRAM cell is 1, as we saw in the question. So now let's just take a look at the operations of both of them. So this is also called a 3T 1C DRAM cell. So what's also called a 3T 1C DRAM cell. So this was one of the first DRAM cell to be used in the industry. First DRAM cell that was used for industry use. And it consists of these three transistors, NMOS transistors, M1, M2, and M3. And also here there is capacitance, CS capacitance, and data is stored here at this node X. This CS capacitance need not to be an external capacitance, so it doesn't it cannot it can be it can or cannot be external capacitance. So it can be an input gate capacitance or parasitic. So typically it's an input gate capacitance and parasitic capacitance. So write operation is quite. Let's just take a look at the write operation first. Write operation is quite similar to the, or should I say, to the 60 SRAM cell as you saw earlier. So whatever data, so be it 0 or 1, we want to store, needs to be put on the bit line 1. So we can write the statement, put the value that we want to write on bit line 1, and after that assert write word line high. So assert write word line high means activating it. So what I said before writing, so whatever data we need to write, we need to put it on bit line 1, and after that we need to assert write word line high. So this needs to be activated. So this is the write word line. WWL stands for write word line, that is connected to the transistor M1. So as this M1 is turned on and we are putting this 0 or 1 accordingly. So if there was if this was initially discharged, and if you are writing 1, so this capacitor via this transistor M1 will be charged to VDD, and if this was 1 and we are writing 0, so this will be discharged. So be it 0 or 1, that will be written here. So it will be either VDD or connected to ground, or nothing will be stored here, VDD or 0. After that we are going forward for the let me just divide it for read operation. For read operation, we will precharge as we did in SRAM. We'll precharge bit line, but which bit line? Bit line 2. We'll precharge bit line 2, and then we will assert read word line. So read word line is this one. So M3 will be asserted and M3 will be turned on based on the value stored here. So if a 0 was stored here, this thing will be off and this thing will be remain, this thing will see no discharge. And if VDD was here stored, this thing will turn on. Similarly, this M2 will turn, this M3 is always on for read operation based on the values of stored at node X. Based on the value at X, M2 will be turned on or off. So when we wrote 1, so this will be turned on, and this capacitor that is here present will see a discharge. This bit line 2 will see a discharge and will be connected to this ground and will see a discharge, and as a result it will just turn to 0 when 1 is stored here, and when 0 is stored here it won't see any discharge. So as you can see, if we wanted to store 1, this will discharge. If we wanted to store 0, this will remain same for a read operation, and as a result this operation is kind of inverting. So whenever we want to whenever we want to refresh the things, so what is the refresh operation? Basically this capacitance sees leakages, and that's why we need to read the state and write the state again. That's why it's called a dynamic. Dynamic basically means we need to refresh states again and again after some time, typically in from 100 microseconds to a few milliseconds. We need to refresh the states again and again, basically reading the states, then writing its invert here. Basically when I'm reading the state 0, this thing is kept at high, so I need to write its invert here, and this will be when we again storing 0, and if 1 was stored here, this thing will discharge, so its invert, that is 1, we need to be writing again. So that is the refresh operation. So read plus write means the refresh. So what is that? Read and put its invert on BL1 and write, that's the refresh operation. And to increase the speed of operation, single-ended sense amplifier is converted, and also here sense amplifier is not a requirement but increase the speed of operation. Also read and write path are here decoupled. Now towards the 1T1C DRAM cell, it consists of a one transistor and one capacitance. So whatever value we want to write, so let's just discuss the write operation first. Whatever value we want to write, we will put it on bit line. So if you want to write 0, we will just connect it to ground. If you want to connect to 1, we'll just put VDD here. So we'll just connect whatever value. So the CBL will be either connected to ground or it will be just charged to VDD. Then we will assert the word line high. This word line will be asserted high. This M1 will be turned on, and charge distribution will take place, and DSCS will be charged and discharged based on the voltage present here. Now for a read operation, this bit line is precharged to VDD. That is simply CBL is precharged to VDD by 2. CBL is precharged to VDD by 2, and word line is added high. And as a result, charge distribution again takes place. And if 0 was stored here, this thing will discharge. And if 1 was stored here, this thing will tend to 1. So what happens here? So this CBL, during read operation, it was precharged to VDD by 2. So if 0 was stored here, this VDD by 2, because of charge distribution between CL and CS after the word line is turned on, as it high, charge distribution will take place and this voltage will slightly decrease at CBL. And if 1 was stored here, this voltage due to charge distribution will slightly increase. Here, sense amplifier is an SST because this delta V is typically around 500 millivolts and it will not push it to back to ground or to VDD. So here sense amplifier is not just a increase the speed of operation, but it's also a requirement. So to bring it down to ground and to take it up to VDD, a sense amplifier is required. Also, this operation is non-inverting as compared to the 3T DRAM cell, which was inverting, and also refresh is also done here because leakages are present. So after few milliseconds, read and write operations are performed again and again. That's why the nature dynamic is present here. So this was just a brief introduction to this. So any doubts, please ask. If not, we can move forward to the MCQs. For more information, you can just refer to the books of, let me just give the complete name of the book. I don't know, VLSI designed by Jan M. Rabai, or you can refer his lectures also. And also you can refer to the semiconductor memories by some book by book titled Semiconductor Memories by Professor Shimangyu. You can also refer to that book if you want more regarding this. Now moving forward to question number 3 of today's live session. It says that in the given circuit, if the control logic inputs are CS complement is equal to 1 and RW complement is equal to 1, then which operation will take place? So let's just consider the truth table. We have CS 0, 0, 1, 1. This truth table you would have seen in your live lecture in your lectures. I'm just writing it again here. So when this is 0, 0, this is 1 and rest are 0. When this is 0, 1, this is 1 and rest are 0. So here when CS complement equal to 1, that implies CS is equal to 0. So based on the truth table, so let's just take a look at the truth table. So CS is equal to 0 and this is equal to 1. So for CS equal to 0 and read write complement is equal to 1, there is only read operation taking place. Only read operation is taking place. So the question asks us which operation was taking place. So based on the truth table, only read operation is taking place. So option A is the correct answer. Now moving forward to question number 4, it states that how many data input and address input lines are required for a 128K cross 16 memory. So let me just repeat the question. How many data input and address input lines are required for a 128K cross 16 memory? So for a memory address input, let's just refer it as P. M is termed as number of location. N is your data input. We have 2 raised to power the number of address input is equal to M. So this thing is equal to 2 raised to power P. M is equal to 128K. So 2 raised to power P is equal to 128 can be simply written as 2 raised to power 7, and 1K is equal to 2 raised to power 10. So that implies 2 raised to power P is equal to 2 raised to power 17, and that thing implies P is equal to 17. Let's just mark it here. And also a memory M cross N is given to be equal to as 128K cross 16. So M is 128K and N is 16, so that implies N is equal to 16. So we need to find out number of data input and address input lines. So data input is N and address input is P. So we need to find out N and P. So N was equal to 16 and P was equal to 17. So our answer is 16 comma 17. So option D is the right answer. Any doubts? Now let's move forward to question number 5, which states that to construct a 1 mega cross 4 memory, the number of 64K cross 4 memory circuit required is. So to construct a 1 mega cross 4 memory, the number of 64K cross memory circuit required is. So this thing, so we have our requirement is 1M cross 4, and we need to use 64K cross 4 memory circuits. So 1M cross 4 can be written by how many what are available, 64K cross 4. So this is simply equal to 1 mega is equal to this is 64K. So we know that 1 mega is equal to 2 to the power 10K. So 2 to the power 10 is equal to 1024K. So this is equal to 1024 by 64. That thing is equal to 64 1, 64 16. So 16 64K cross, so 16 64K cross 4 memory circuits will be required. So answer is 16. Now we have this question number 6. So it states that in the given circuit diagram of a PLA unit, that is programmable logic array, the expression for F1 and F2 is given by. So we need to find out the expression for F1 and F2 based on the given circuit diagram. So let me just increase the size first. It's quite small. Yeah, I think it's fine now. So let's just do it step by step. So this is A, input A connected to the NOT gate and buffer here. So this line will be A as given, and this line will be A complement. Let me just mark it here also. This is A complement. Similarly, this is B complement, and this is B, and this is C complement, and this is C. Correct? So let's just write first. These are the AND gates, and the numbers are also given to them. These are 1, 2, 3, 4. So AND gate number 1. So input to AND gate number 1 is it's A complement C complement, and its output will be A complement dot C complement. So inputs are here. I will write input to AND gates. Inputs are A complement comma C complement, and as a result, the output will be A complement comma C complement. So this line will be A complement comma C complement. Now this was one. Now input to AND gate number 2. So it's, let's just start from the right hand side first. So it's A, then it's B, and finally it's C. So input to the AND gate 2 is ABC, and my output will be A, B, C. Correct? So let's just mark this line as A, B, C. Then I have my AND gate number 3. Its inputs are B complement comma C complement. So let's just write as B complement comma C complement, and my output will be their AND operation, that is B complement C complement. Fine. And finally, the AND gate number 4 is connected to the inputs A and C. Right? These are inputs A and C, and my output will be A, C. And let's mark this as AC, and this was previously B complement C complement. So the AND lines are done. Now just take a look at the input to the OR gates. This is OR, this is AND, this is OR. So this is 1 and this is 2. So 1 is connected to, its inputs are A, B, C, comma B complement, C complement. As you can see here and here. In fact, 3 inputs are there, and third one is AC complement. So my output will be A, B, C plus B complement, C complement plus A, C complement, A complement, C complement. And now my OR gate 2, its inputs are AC and its inputs are ABC. Right? So my output will be ABC plus AC. Now these are connected to the OR gates F2. One output of OR gate 1 is connected to F2, and output of OR gate 2 is connected to F1. So let's just first write the F1. So F1 is simply equal to output of 2 or 2 XOR with 1. Now here I will write XOR gates truth table. So we have 0, 0. This is input X and this is Y. So this is output 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. So one of the inputs is 1, whenever one of the inputs is 1, the output of the OR gate is complement of the other input. So see, Y is equal to 0, output is equal to 1, Y is equal to 1, output is equal to 0. So F1 will be equal to output of OR2 complement. So F1 will be equal to ABC plus AC whole complement, right? And F2 is equal to output of OR gate 1 XOR with 0. So whenever one of the input is 0 to the OR gate, its output is simply equal to the other input. So output here is 0 when y is equal to 0, output is 1 when y is equal to 1, based on the other input being 0. So this thing will be equal to output of OR gate 1, and that thing is equal to ABC plus B complement C complement plus A complement C complement. Now the answers are given in midterms. We need to find out the midterms first. Let me just first admit the participant and then we can find the midterms. So we have got expressions for F1 and F2. We need to find the what should I call the midterms. So let me just use the new slide here. So F1 came out to be F1 came out to be ABC plus AC whole complement, right? So we can trim it down. We can just write AC. You can just write this thing as AC 1 plus B whole complement. 1 plus B is simply 1. So this thing is equal to AC whole complement. F1 is equal to AC whole complement, and we can just write it as A complement plus C complement. Now we need to write its midterm form. So what we'll do, we'll just write A complement B plus B complement plus C complement B plus B complement, right? So this is A complement B plus A complement B complement plus B complement B C complement plus B complement C complement, right? Now we'll write simply using the same methodology here. I'm just skipping some steps. So A complement B C plus A complement B C complement plus A complement B complement C plus A complement B complement C complement plus A B C complement plus A complement B C complement plus A B complement C complement plus A complement B complement C complement. Now let's just check whether any terms are repeating. So A complement B C is not repeating. A complement B C complement is not repeating. A complement B complement C, A complement B complement C is repeating. I think it should be repeating. A complement B, A complement B complement C complement. A complement B complement C complement is repeating, and A complement B C complement is repeating. Yeah. So two terms are repeating, and finally we have A complement B C plus A complement B C complement plus A complement B complement C plus A complement B complement C complement plus A B C complement plus A B complement C complement. So in terms of midterms, we can write summation midterms. So this thing is 3, this thing is 2, this thing is 1, this thing is 0, this thing is 6, and this thing is 4. So the midterms are 0, 1, 2, 3, 4, 6. 0, 1, 2, 3, 4, 6. So only one of the option is having f1 equal to 0, 1, 2, 3, 4. That's option A. So based on only F1, we can just check the correct answer. But I'll just show for F2 also. So F2 is, I'll just write here, F2 is equal to A complement C complement plus ABC plus B complement C complement. So we can write it as A complement B C complement plus A complement B complement C complement plus ABC, then A complement B complement C complement plus A B complement C complement. This and this is repeating. So finally we have summation of minterms. This is what is this? This is 2, this is 0, this is 7, and this is 4. So summation of 0, 2, 4, 7. So option A was the correct answer. So any doubts? Please ask in. If not, we can move forward to next question. But let me just take a quick break first. I'm just taking a break of a couple of minutes, and we can then after we can resume. So we can resume. So next we have to discuss question number 7. Yeah, we have to discuss question number 7. So question number 7 states that which of the following statement or statements is or are true. So we need to check which of the statements are true. So the statement 1 reads that the main memory of a computer system must be non-volatile. So the main memory of a computer must be non-volatile. The statement 2, the data memory can be built using either ROM or RAM. Number 3, write enable time is the time to be allowed between placement of stable address and availability of stale data. And finally, SRAM using CMOS uses cross-coupled inverters for basic memory cell. So let's just examine each of the statements, then we can decide with our answer. The statement 1, it reads as the main memory of a computer system must be non-volatile. So the main memory of a computer is typically RAM. The main memory of a computer is RAM, which is typically volatile. So the statement 1 is false. So this is false. So statement 2, it says that data memory can be built using either ROM or ROM. So the data memory needs to have both the write capability as well as the read capability. But however, ROM has only the read capability, so the data memory can be built using either ROM or ROM is a false statement. Now the statement 3 reads as write enable time is the time to be allowed between placement of stable address and availability of stable data. Write time, this is a wrong statement. Write time is defined as the minimum time required to write to remain require the write to remain enabled. So this is also false. And statement 4 it states that SRAM using CMOS uses cross-coupled inverters for basic memory cells. So this is earlier where we had true cross-coupled inverters. So this is true. So only statement 4 is true and that is option D is correct. So if you are preparing for any competitive exam, so you can just see only four, you would have just seen that only four statement was correct and you would have marked the option D right away without looking for the another option because 4 was definitely correct and it needed to be present in any of the options. So only it was present in option D only, so only D is correct. Now question number 8. It states that suppose you are using linear addressing in a memory IC. The IC has a memory of 1024 cross 4 bits, that is 4 bits of data input output. You are then redesigning the IC to have matrix addressing configuration. The total number of input pins to the address decoder for both linear addressing and matrix addressing are. So we need to find out the address pin required for both linear addressing and matrix addressing. So we have for linear addressing. So for linear addressing, the number of inputs to the address decoder is log 2 1024, that is equal to 10. And for matrix addressing, the number of inputs to the row address decoder is equal to 10 by 2, that is 5. Similarly, for the column decoder, number of inputs is also 5. So that means for matrix addressing also the total number of input pins, total number of input pins to the address decoder is 5 plus 5, that is equal to 10. So both for linear addressing and matrix addressing, the number of input pins to the address decoder is 10 and 10, that is option D. So for more about this, you can refer to lecture number 56, slide 8. Now question number 9, it states that suppose you need to choose a suitable memory IC for your circuit design and the inventory only has IC 2114 and 2115 available. But your requirement is for a word organized separate input output memory. Which of the above two memory ICs are suitable for the circuit? So we are having the limitations of only two ICs, that is 2114 and 2115, and the requirement is for a word organized separate input output memory. So we need to figure out which one of the IC will be suitable for our circuit. So before proceeding, this IC2114 is a word organized word organized and common input output type memory IC. And IC 2115 is a bit organized and having separate input output type. So our requirement was for a word organized separate input type memory. None of the two ICs meet the requirement, so none of them are suitable because this was a word organized but had common type. This was a separate but had a bit organization. So none of them meet the requirements, so none of them is suitable for our circuit. Now towards question number 10, it states that in the following 3T configuration DRAM cell, you need to first write a single binary digit D in and then read it from terminal Y. Assume the parasitic capacitor for which of the polarities we need to find out the correct polarities of W, R, and Y terminals. So we need to write the data, and as I saw earlier, when data needs to be written, this word line or right here is W needs to be asserted high. So this will be high. Actually, options are missing. I have not written options here, but this will be high. This read. So this for a read, we need to also assert it high, so R will also be high. And dn1 was written here, and so the polarity for y will be, so I told you this 3t1c is an inverting operation, so as 1 was written here, so 0 will be present here, so this will be low. So the correct polarities are high, high, and low. Actually, I forgot to write the options here, but I remember the answer to this question is high, high, and low. This was written high and 1 was written here, then this was written high, and this Y will be discharged via these two transistors, high, high, and low. Option question number 10. Any questions so far? If not, we can continue with question number 11 of today's live session. So this says that suppose we want to design a memory block like IC2114 1024 plus 4-bit memory chip using IC74201 256 cos 1 bits memory chip using both address and data range expansion. How many IC7421 are required for the design? So IC2114 has log to the log 1024 to the base 2 bits address bits, so that is 10 address bits. IC74201 has log 256 to the base 2, that is 8 address bits. For expansion, range expansion, we need 2 raised power 10 by 8, 2 raised power 8, that is 2 raised power 10 minus 8, 4, 2 raised power 10 minus 8, that is 2 raised power 2, that is we need 4 IC7421. 201, and for each sub expansion we further need 4 IC 74201. So therefore for data range expansion, total number of, so for each sub expansion we further need 4 IC 744 IC 7401 for data range expansion. So the total number of ICs required will be 4 cross 4, that is 4 multiplied by 4, that is equal to 16. So option C is the correct answer. Now question number 12, it states that which of the following statements are true? It says that EEPROM uses ultraviolet light through quartz window to erase stored charges. Then is in PLA AND array is fixed or array is programmable. Number 3, in PAL OR array is fixed and AND array is programmable. And in option 4, DRAM has higher packaging density than SRAM. So let's just go examine each statements and see which of the following are true. It said that EEPROM uses ultraviolet light to cross window to erase stored charges. This is false. This EEPROM uses, not EEPROM. So EEPROM uses ultraviolet light through quartz window to erase stored charges. EEPROM uses electrical signals to erase charges. So this is false. In PLA, AND array is fixed or array is programmable. This is also false. This should be EEPROM. This is false. Not only AND, not only OR, but both are programmable. In PAL, OR array is fixed and array is programmable. This is true. DRAM, that is dynamic random access memory, has higher packaging density than SRAM. As you saw earlier, it has less number of transistors. So this is also correct. So 3 and 4 are true. Now moving forward to question number 13. It states that which of the following statement is true? In a random access memory, the access time depends on the location of the word. In a random access memory, the access time is independent of the location of the word. In a sequential memory, the access time is independent of the location of the word. Access time is same for location in both the random and sequential memories. Option B is correct. In random access memory, the access time is independent of the location of the word. In a sequential memory, it is dependent on the location of the word. For a random access memory, it is independent on the location of the word. Now, coming forward to this question number 14. Now, I think the 3-4 questions are simply one word type answer because this topic was mostly theoretical and only these type of questions were I was able to construct with keeping syllabus in mind. So SRAM memory offers A, high density, B, lower cost, C, high speed, and D, low power consumption. So the SRAM cell, if you can see, is the fastest cell and is very close to the processor. So this offers high speed. This is not dense. It's not lower cost. SRAMs are highly costly, and power consumption is slightly high. So the only thing that SRAM memory offers is high speed. Next, question 15. A DRAM cell stores the binary information on A, the external capacitor connected to it, B, the parasitic capacitor of MOS transistor, C, the external inductor connected to it, and D, the resistor. As you saw earlier in 3T, 1C and 1T1C structure, the data is stored on the capacitor, that is from the parasitic capacitor or gate capacitor of a MOS transistor. So option B. Now, question number 16. It says that a memory unit 1024 cross 64 is specified by the number of words times the number of bits per word. How many address lines are needed for the given memory unit? So a memory unit is typically represented by 2 raised to power k cross n. So this is a representation of a memory unit, where this 2 raised to power k represents the number of words, n represents number of bits per word, and k represents number of address lines needed to access a particular word. So we have a representation like 2 raised to power k cross n, and here we have it to be equal to 1024 cross 64. So we can write it like this: 2 raised to power k cross n is equal to, this 1024 can be written as 2 raised to power 10 cross 64. So that implies k is equal to 10. So the number of address lines needed for the given memory unit is 10. We have another question. I think it's quite similar to the previous question. It states that which of the following statement is false? Number A, option A, PAL has programmable AND array and fixed OR array. Option B, PROM has fixed AND array and programmable OR array. Option C, PAL has programmable AND array and programmable OR array. And option D, in PLA, both AND and OR arrays can be programmed. So as you saw earlier, this thing is incorrect. PAL has both programmed and programmable OR array. As you saw here, PAL, in PAL, OR array is fixed and array is programmable. So this was the incorrect statement. Now towards the last question of today's live session, it says that identify the functions f1, f2, f3 implemented by the following PLA circuit. So we need to find out the function implemented by the following PLA circuit. So before proceeding, let's just mark the outputs coming from this inverter and buffer. So this thing will be, I guess, this will be A complement. Let's just write it here. This will be A, this will be B complement, this will be B, this will be C complement, and this will be C. And let's just mark them also 1, 2, 3, 4. These as 1, 2, 3. So here I will write input to AND gates. Here I will write their outputs. Here I'll just write AND. So input to AND gate. So input to AND gate 1. So input to AND gate 1 is B complement and C complement. That means output is B complement, C complement. Then I have number 2. Its input is B complement and B complement and B. That means B complement ANDed with B means 0. Then I have number 3. Its input is A complement, B, then C complement, and we can write it as, its output can be written as A complement, B, C complement. Then number 4, we have A here, then we have B here, then we have C. So output will be simply A, B, C. Now for the OR gates, let's just write here the inputs and the outputs. So output, so this is OR gate. So OR gate number 1, It has inputs, these, let me just mark them also here. A complement, B, C complement, this is 0, this is B complement, C complement. For clarity, I'm writing them A, B, C. So input to OR gate number 1. So let's just label this as 1 because then it will be connected to the output also as 1. So this is 2 and this is 3. So input to OR gate 1 is B complement, C complement, 0 and ABC. So output will be ABC plus B complement, C complement. Then OR gate 2 has inputs as 0 and this one, this is 0 and this one, so this is A, B, C. Output will be simply equal to A, B, C. Then 3, so 3 is this one, B complement, C complement, and also A complement, B, C complement. So output will be B complement, C complement plus A complement, B, C complement. So that implies F1 will be equal to A, B, C plus B complement, C complement. F2 will be equal to A, B, C, and F3 will be equal to B complement, C complement plus A complement, B, C complement. So F1 is equal to A, B, C, B complement, C complement. F2 is equal to A, B, C, and F3 is equal to B complement, C complement, A complement, B, C complement. So option B is the correct answer. So that was all for today's live session. If there are any doubts, please type in. And also thank you for attending the live sessions and watching the recordings. I wish you all the best for your exams, and hopefully we can meet with the next course in the next sem. So if you have any doubts, please type in the chat box or you can use your microphone. Otherwise, the session is over. You're welcome. So I think there are no questions. So let me just give the complete name of the book I mentioned earlier. Let me just give the complete name. So the name of the book. Let me just. So you can refer to chapter number 12 of the book. Chapter number 12 of the book. Let me just give the complete name. Chapter number 12 of the book Digital Integrated Circuits, A Design Perspective from John M. Bright from UC Berkeley. And if you want to get, if you also want to refer to some other memories, so you can just refer to the book Semiconductor Memories and Circuits by Professor Shimangyu, 2022 edition. This is a pretty new book. You can also refer to that also. So these two books I recommend if you want to look more into DRAMs and SRAMs. So that was all for today's live session. Thank you. See you soon.